Now we go for question number 9. What is it? Look, to find magnetic field due to extremely long, very thin current carrying straight wire using Amperes circuital law. My dears, if you remembered in this chapter, in the beginning we had studied about B.S.SHAH's law. Using B.S.SHAH's law, we had obtained magnetic field at some perpendicular distance y from extremely thin, extremely long current carrying straight wire. Remember that result? That result was B equals to mu 0 I upon 2 pi y. Remember this result? Fine. But the derivation was very long at that time. But now the same formula we will obtain through a very short derivation using Amperes circuital law. How? I am showing you. Consider infinitely long, extremely thin current carrying straight wire which carries current I, suppose vertically upwards. Right? Now you know current is nothing but a source of magnetic field. So in the surrounding region you will have magnetic field, that is sure. So first of all you select some point of observation where you want to determine the magnetic field. Suppose that point is this, correct? Point Q. Now in case of magnetic field produced by extremely thin current carrying straight wire, infinitely long, you know the magnetic field which is produced surrounding to that wire has magnetic field lines in the form of circular lines, correct? It has circular magnetic field lines, and out of those circular magnetic field lines, I am just showing only one magnetic field line passing through point Q whose center is on the wire, correct? Fine. So this is circular magnetic field line, correct? This point which is the center of this circular magnetic field line is on the wire itself, and this is the point on the magnetic field line. Now tell me, if you have thought of infinitely long straight wire, then tell me how to find these positions of points P, Q and R. Don't you find those positions, those points quite symmetric? What do you mean by symmetric positions? What do you mean by symmetric points? The meaning is that whatever is the physical condition here, same must be physical conditions here and here. Then those points are called symmetric points. How the physical conditions are same? Very simple. Whatever is the perpendicular distance of this point from this wire, same is the perpendicular distance from this wire of this point. Same is the perpendicular distance of this point from this wire, correct? All these three perpendicular distances are same. One more thing, whatever magnitude of magnetic field you can expect at this point, same magnitude of magnetic field you can expect at these points also. That is why in all respects the positions of all these points are symmetric. Okay? Out of many such symmetric points, I have just considered only one symmetric point, let it be point Q. Now because point Q is lying on the magnetic field line, the direction of magnetic field at this very point will be in the direction of tangent drawn to this magnetic field line at this very point. Okay? And because it is circular, for a circle, come on, tangent is always perpendicular to radius, correct? So this tangent is perpendicular to this local radius at this very point, correct? Now when you take line integration of magnetic field on this closed path, which is a planar closed loop, we call it Amperian loop, at that time you can divide this entire length into extremely small length element vectors. And at this point you can see the direction of length element vector will be in the same direction of tangent, that is in the direction of vector B, correct? At different points direction of vector B is different, but at a given point if you think of direction of vector B and vector dl, they are in the same direction. Okay? So at each point on the considered circular Amperian loop, locally vector B and vector dl are parallel, they are in the same direction. And now to find out magnetic field at this very point, you just apply Amperes circuital law. It is closed line integration of magnetic field is equal to product of mu 0 and sigma I. The same mathematical form I have written here, no change. Okay? Simplify now. Closed line integration as it is. Vector B dot vector dl means B into dl into cos theta. B into dl into cos theta, where theta is angle between these two. Just now I explained, at each point the angle between vector B and vector dl, because they point in the same direction, that angle will be 0 degree. I am putting 0 degree here. Mu 0 as it is, sigma I means algebraic summation of electric currents enclosed by considered closed loop, enclosed by considered Amperian loop. Now this is the Amperian loop which encloses only one current right now, and that current is I, correct. When you will require to take algebraic summation, provided you have more than one currents. Here we have only single current. So sigma I can be written as I only, and now cos 0 is 1, and because the magnitude of magnetic field at all these points which are equidistant from this wire is same, then value of B is taken constant. It is taken now out of the symbol of integration. B is taken out, closed integration of dl, and cos 0 is 1, mu 0 into I as it is. Tell me now, B as it is. What about closed integration of dl? Closed integration of dl means summation of lengths of all the length elements taken over considered closed loop. If you start from this point, you must come back to the same point by traversing over the same circular magnetic field line or same circular Amperian loop. Come on, when you just add up all these lengths of all these length elements which are arranged continuously over the rim of that Amperian loop, over the circumference of that Amperian loop, that total, that summation will give you circumference of that circle. And for any circle, what is the formula of circumference? It is 2 pi into radius, 2 pi into radius. Radius is right now small y. So now this value will give me circumference, which is 2 pi into radius. Radius is right now small y. Right hand side as it is. Find out B now. Transfer this term in the denominator on right hand side. It will be mu 0 I upon 2 pi y. Mu 0 I upon 2 pi y. Mu 0 I upon 2 pi y. Correct? And now tell me, same formula we had obtained using B.S.SHAH law also, but that derivation was very long. Here within 2-3 steps we are getting the same formula. Okay? Now think of relation between B and Y. Come on, B is inversely proportional to perpendicular distance from the extremely long, extremely thin current carrying straight wire. Correct? Before we go for next question, let me just tell you about one fact. To please remember, it will be very useful to you in the numericals. When you consider this wire to be very thin wire, then all the points on the wire can be taken on the axis of the wire. The wire is considered that much thin, and for those points which are on the axis of the wire, remember there is no magnetic field due to the current passing through the wire. Why? Remember, wherever the source is present at the same position, you will not have corresponding field. Wherever electric charge is present at the same point, at the same position, you will have no electric field produced by that particular charge. Correct? You will have electric field only in the surrounding region. In the surrounding region, not at the position of the charge. Similarly, wherever there is electric current at the same position, you cannot expect magnetic field. Yes, you will have magnetic field, but in the surrounding region. What was the conclusion made by Mr. Oersted? He had said that whenever we pass current through a conducting wire, we have production of magnetic field in the surrounding region, not on the axis of the wire. Correct? So remember, if you have got wire which is very thin, and if you are passing the current through that wire, you will have no magnetic field at the points on the axis of that wire. Correct? You will have magnetic field in the surrounding region, but not on the wire itself. Okay? But if this wire is considered very thick wire, then surrounding to the axis of the wire, even inside the wire, we have magnetic field. But how much is that magnetic field? I am showing you. So let us go for that question now. Question number 10. To find magnetic field inside current carrying extremely long, thick straight wire. Consider this thick wire to be extended up to infinity theoretically, and practically very long thick wire. Compared to this, you can see this wire is very thick. The radius of circular cross section of this wire, let it be small a. Correct? Now we are interested in finding out the magnetic field at some inside point. Okay. Then you please consider this Amperian loop inside the wire. Okay. Because it is inside the wire, this radius will be naturally smaller than this radius. If this radius is small r, it is smaller than a. I am writing here r less than a. Got it? Now, how to get magnetic field at this point or at any point on this inside circular Amperian loop? Okay, I am showing you. See, in this entire thick wire, the electric current density is same everywhere, whether you consider bigger cross section or you consider smaller cross section, correct? It is same everywhere, and let it be capital J, which is electric current density. What is this formula? Current upon that area which is perpendicular direction of current. If current is I, then divided by, I should write perpendicular cross sectional area. Perpendicular to this current, it is this cross section. Okay, fine. Now, this cross sectional I have written here, this cross sectional area, because it has radius a. What about area of a circle? Pi into radius square, correct? Where I is the total current passing through entire thick wire. But now, if I consider only this much cross sectional area, then I should write down the current passing through this much area and let it be IE, which is enclosed current, enclosed by this smaller Amperian loop, correct? It is smaller than this, I am giving different symbol IE, that is enclosed current, divided by corresponding cross sectional area. Area of this circle will be pi into radius square, but radius is smaller, so I am writing here pi into radius square, correct? Find out IE now, pi will cancel, take this up, so it is I into r square upon a square, I into r square upon a square, fine. Now apply Amperes circuital law. What was the mathematical form? Closed line integration of magnetic field is equal to product of permeability of vacuum and the algebraic summation of electric currents enclosed by considered Amperian loop, correct? Now, because we are talking about magnetic field at some inside point, I just show its magnitude by symbol BI. I stands for inside, okay? Come on, when you expand this, it will be B into dl into cos theta. Theta, as I explained earlier, it is 0 degree, because at whichever point you want to find out direction of magnetic field, at the same point if you find out direction of length the element vector, then vector B and vector dl, because they have same direction, theta will be 0 degree, mu 0 as it is. What is sigma I? Algebraic summation of electric currents enclosed by considered Amperian loop. Considered Amperian loop is this, then whatever is the current passing through this much cross sectional area, that is called enclosed current, and which we had shown by symbol IE, okay? So this is enclosed current, it is IE, enclosed current. Now this is the magnetic field at some inside point, so I am putting symbol BI, and because the magnitude of magnetic field at all these points are same, then BI is constant, can be taken out of the symbol of integration. BI is taken out, closed line integration as it is, cos 0 is 1, mu 0 as it is. What about IE? IE is, come on, I into r square upon a square, I into r square upon a square. Come on, BI as it is, closed integration of dl means summation of lengths of all the length element vectors considered over given Amperian loop. Given Amperian loop is right now this one, and when you take the summation of lengths of all the length elements, it will give you circumference of the circle. For a circle of radius small r, what is the circumference? 2 pi r. So this is nothing but 2 pi r, and this right hand side as it is. Got it? Come on, simplify now. 1 r is getting cancelled. What is left? Find out BI from that. Make it subject of the equation. You will get in mu 0 I upon 2 pi a square, and because 1 r was cancelled, that r I am writing outside the bracket, because this bracketed part is constant. In a given condition, this bracketed part is constant, so BI is proportional to r. When BI is proportional to r, what does it mean? For any inside point, the magnitude of magnetic field is directly proportional to perpendicular distance of that point from the axis of thick wire, correct. So, when this will increase proportionally. Now, let us plot a graph of magnetic field versus distance from the axis of thick wire. What is the nature of the graph? I am showing you. Come on. When you consider R less than A, you are inside the wire. When R is less than A, you are inside the wire. And for that region, the graph of B versus R is a straight line, because BI is proportional to R. This is linear relationship. That is why the graph is a straight line, correct. Then when you take R greater than A, then you will be talking about outside region. For a region outside the current carrying wire, the relation between B and perpendicular distance is inverse proportionality. That is why I am putting here B proportional to 1 upon R, inverse proportionality. And because it is outside point, I am just putting symbol BO, O for outside, So, there BO is inversely proportional to the perpendicular distance, and that distance is greater than the radius of given thick wire, got it. Now, in that case, the graph is hyperbola like this, correct. This is called non-linear relationship, because it is hyperbola, it is a curve. Here it is linear relationship, got it. And this is the point where R is equal to A. When R is equal to A, you are going to take a point on the surface of the thick wire. At that time, the magnetic field is maximum at all the points. Among all the points, this is that point where magnetic field is maximum, and that maximum magnetic field I just showed by symbol B maximum. And how to find out that B maximum? Very simple. You just put R equal to A. Put R equal to A here. When you put A here, one A is getting cancelled. Left is mu 0 I upon 2 pi A, mu 0 I upon 2 pi A, correct. So, when you start from the center on the axis of a thick current carrying wire, which is considered extremely long, here exactly magnetic field is 0. But when you move away from this axis till you reach the surface, magnetic field increases proportionally, with direct proportionality with the perpendicular distance, correct. But when you are on the surface, the maximum magnetic field you can expect, and it is mu 0 I upon 2 pi A. And further, if you move, you will be moving outside the thick wire. At that time, magnetic field at any outside point is decreasing with the increase in distance R, okay, with this relation BO proportional to 1 upon R, got it. Come on, my dears, we proceed further in chapter number 4. We now go for question number 11. To find magnetic field inside extremely long current carrying solenoid using Amperes circuital law. My dears, last time we had studied about solenoid. Remember the definition? If any isolated conducting wire is wound to form a cylindrical coil with a helical shape, then it is called a solenoid, correct? Fine. Compared to the radius of cross section of a solenoid, if its length is very large, then we call it extremely long solenoid, correct? For such a solenoid, we find practically that when we pass some current through the winding of the solenoid, we get magnetic field almost inside the solenoid. We do not get practically any magnetic field outside the solenoid, correct? But it is true for extremely long solenoid. Now, we are interested in finding out the intensity of magnetic field which is produced inside the solenoid, okay. Let us find it using Amperes circuital law. How? I am showing you. First of all, consider the cross section of a solenoid. When you take the cross section, you can see these dots which I have shown in the upper part. Each dot indicates the turn which is coming out of the plane of the figure perpendicularly. Coming out, then dot, going inside, then cross, correct? Or you may say each dot indicates current passing through that turn which comes out of the plane of the figure perpendicularly. and each cross indicates that current which is going inside the plane of the figure perpendicularly. Got it? Fine. Now, whenever we are applying Ampere's circuit law, first we consider some proper Amperian loop, which is a planar closed loop. Here in this case, we just select rectangular Amperian loop, and that rectangular loop is PQRSP, correct? It is a closed loop, fine. Now this much length we assume to be small l, okay? Now what we want? We want line integration of magnetic field in each part of this Amperian loop. Let us find it one by one. Line integration of magnetic field, that is integration vector B dot vector dl. Now that line integration, when you find it from P to Q, then from R to S, and then from S to P, we find it to be 0. Each of these three values is 0. Why it is 0? I am showing you. When you take line integration of magnetic field from P to Q, then from P to Q, then look here, this much part is outside the long solenoid, and for extremely long solenoid in the outer region there is no magnetic field, so B is 0. Because B is 0, this whole term will be 0, correct? And so far this part is concerned, you can see in this part the vector dl is vertically downwards and vector B will be towards right hand side if you are passing current this way, correct? If you are passing current through the winding of solenoid this way, then you are going to have magnetic field towards right hand side. So in this much part it will so happen, the situation will be like this. This is vector dl vertically downwards and this is vector B, correct? Angle between vector dl and vector B, you can say it is 90 degree, and because angle between these two vectors is 90 degree, come on, that dot product will be 0, correct? Similarly, when you go from R to S, in this much part, vector dl from R to S, vector dl is vertically upwards and vector B is towards the right hand side, correct? And because vector B and vector dl are mutually perpendicular, dot product will be 0. And so far this part is concerned, you can say it is outside the solenoid. Outside the solenoid there is no magnetic field. When B is 0, naturally this whole term will be 0, correct? And so far this part is concerned from S to P, come on, that entire part is outside the solenoid where there is no magnetic field. So when B is 0, naturally this term will be 0, correct? So for all these three values of line integration of magnetic field, either B is 0 or vector B is perpendicular to vector dl. When B is 0 or vector B is perpendicular to vector dl, naturally all these values will be 0, correct? But still there is one part left out in which line integration of magnetic field is not 0. That part is from Q to R, from Q to R, correct? Now let us find out that line integration. Come on, line integration of magnetic field from Q to R. Come on, this line integration as it is. Vector B dot vector dl means B into dl into cos theta. B into dl into cos theta, where theta is angle between vector B and vector dl. Come on, vector B at present it is toward right hand side, and when you move from Q to R, the direction of length element vector will be like this, toward right hand side, right? I mean to say vector dl and vector B both are pointing in the same direction, and because these two vectors have got same direction, angle between them will be 0 degree, cos 0 is 1. And the strength of magnetic field at each of these points on the line segment QR is same, constant, and because value of B is constant, you can take it out of the symbol of integration. So B is taken out, left is now integration dl from Q to R. Now this B as it is, what do you mean by integration dl? Integration dl means summation of lengths of all the length elements chosen over this line segment Q to R, correct? Naturally, when you add up the lengths of all the length elements from Q to R, it will give you this much length, and this much length is nothing but small l. So this integration dl value is right now small l, correct? Now I want closed line integration of magnetic field over Amperian loop P to Q to R to S to P, correct? But out of these 4 parts, on 3 parts that line integration came out to be 0, only one part was left out in which line integration is not 0, and that was part from Q to R. From Q to R, vector B dot vector dl, correct? And its value we had found out, it was B into L, B into L. And now apply Ampere's circuit law. What was the mathematical form? Closed line integration of magnetic field is just equal to product of mu 0 and sigma I. Same result I have written here, correct? Come on. Closed line integration of magnetic field, we have found out it is B into L, B into L. This mu 0 as it is. What do you mean by sigma I? Algebraic summation of electric currents enclosed by considered Amperian loop. Considered Amperian loop is this, and the amount of current which is enclosed by this loop is from this end to this end. You can see there are so many turns here in this much length. Let that number of turns be capital N. Now through each turn there is a current capital I. Through one turn, if the current is I, then through n number of turns, what will be total current? N into I, N into I. That's why I am writing here N into I. This much amount of current is enclosed by this considered Amperian loop, correct? Fine. Now you just do one thing, take this L down. So B equals to mu 0 into N upon L into I. Now tell me, what is this? Number of turns per unit length of a solenoid. Let it be shown by symbol small n, correct? So this mu 0 as it is, this I just replace it by small n and capital I as it is. B equals to mu 0 n I. Remember the same result we had obtained earlier using B.S.SHAH law, but the derivation was very long. Here this derivation is very short, okay? Fine. But mind well, this expression you can use only for extremely long current carrying solenoid, correct? And for extremely long current carrying solenoid, at any inside point, magnetic field has same magnitude and same direction also. If magnitude is same, direction is same, then you can say that magnetic field is uniform. And for uniform magnetic field, we are supposed to show magnetic field lines parallel to each other. Not only that, the perpendicular separation between each two consecutive lines must be also same. That's why I am showing that uniform magnetic field inside this extremely long current carrying solenoid. Got it? Fine. We now go for next question number 12. It is about short note on toroid. What is a toroid? Toroid is a special device in which when we pass current through the winding of that device, we get magnetic field in the confined region having magnetic field lines which are circular. That sort of device is called a toroid. Now how it is prepared? Very simple. If you join two ends of a solenoid to form a circular construction, then that construction is called a toroid. How does it appear? I am showing you. Look, last time I had showed you this sort of solenoid, remembered? Now, if you join the two ends of solenoid to form a circular coil, then it will appear like this, correct? And this particular circular coil is known as toroid. I would like to show this thing to you very clearly. So I am just coming closer, okay? Look, this is the toroid, correct? Its shape is like inflated tube. Got it? my dears, this shape is called donut shape. Donut shape. Here it is. Donut shape. There is one food item which is available in the bakery called donut, and it has this sort of shape. Okay. This shape very much resembles with one more food item which is South Indian item. It is mendu vada. It is mendu vada. Okay. The shape is similar to that. Okay. Or you may compare it with inflated tube of a tire. Inflated means that tube of a tire which is filled with air. Okay. That shape is the same. Okay. It is called a toroid. Fine. Now, this is called winding of a toroid. The turns are known as winding of a toroid, and whatever region is enclosed by this winding is called toroidal region. Toroidal region. Here it is. Look. Now I am showing you that toroid in the figure which I have drawn here. Look. Here is the circular tube, inflated tube, correct? This is the winding. This winding is done with the help of isolated conducting wire, correct? Isolated conducting wire means a wire on which some layer of non-conducting substance is applied. It has a coating of non-conducting substance. Okay, fine. That wire is wound very closely, and when you wind it very closely, each turn would more or less like a circular turn. Actually, it has helical shape here. Okay. Actually, it is to be wound continuously, but I am showing you few number of turns. Okay. That's why I am showing some separation here between two consecutive turns. Now, through that winding, we pass some current. We pass some current. Fine. When we pass current through this winding, correct, it so happens for ideal toroid in which the turns can be taken as circular, it so happens we get magnetic field only inside the tube. Only inside the tube. That is the region which is enclosed by this toroidal winding. That region is known as toroidal region. Toroidal region. Okay. So, for an ideal toroid, the magnetic field is obtained only inside the toroidal region. That is inside this circular tube. Got it? Fine. For this region and for this region, that is outside the toroidal region, we don't get any magnetic field. Fine. But what is the intensity of that magnetic field which is obtained in the toroidal region, that we want to find out. Now consider few circular turns which are wound very closely to form a thin circular ring. And through a circular ring, when you pass current this way, tell me, don't you expect magnetic field in this direction? Yes. Remember that law of right hand thumb rule. What was that? Hold the axis of current carrying thin circular ring in the right hand palm such that fingers should take the turn in the direction of current. Then whatever is the direction shown by the thumb gives us direction of magnetic field. And same way, if you find out direction of magnetic field at this very point, it will be in the direction of tangent drawn to this circle at this very point. Okay. Not only at this point, at each point on this circle, if you draw a tangent, it will give you direction of magnetic field locally. Now, such a characteristic curve, the tangent drawn at every point on which is giving us direction of magnetic field is known as magnetic field line. That's why the same circle can be taken as magnetic field line. Fine. So, this is circular magnetic field line. Got it? Fine. Now, for that circular magnetic field line, suppose radius is r, which is also called average radius of a toroid. Average radius of a toroid. Okay. Now, we want to have the line integration of this magnetic field over this closed path. So, right now this closed path we take as Amperian loop, which is nothing but circular magnetic field line. Okay? Then tell me, you will divide this entire length into extremely small length elements, and then out of such many length element vectors, one length element vector as a specimen I have shown here at point P, correct? And that length element vector will have direction of tangent this way, that is in the same direction of magnetic field at that very point. Not only at this point, at each point on this circular magnetic field line, it so happens the direction of vector B and vector dl come out to be in the same direction. And because vector B and vector dl have same direction at each point, angle between them can be taken as 0 degree. Angle between these two can be taken as 0 degree. Fine. Now, apply Amperes circuital law. Closed line integration of magnetic field taken over considered Amperian loop is equal to product of mu 0 and sigma I. Correct? That everybody knows. Come on. This integration as it is, vector B dot vector dl means B into dl into cos theta. B into dl into cos theta, where theta is angle between vector B and vector dl. I explained you earlier, vector B and vector dl point in the same direction at each point on this circular magnetic field line or at each point on this Amperian loop, correct? And because they got same direction, angle between them will be 0 degree. Mu 0 as it is. What do you mean by sigma I? It is the algebraic summation of electric currents enclosed by considered Amperian loop. Right now considered Amperian loop is this, and you can see it encloses all these currents which are passing through total number of turns which are wound over the toroid, correct? And that total number, suppose it is capital N. Through one turn, if the current passing is capital I, then through capital N number of turns, what will be total current? Capital N into capital I. Capital N into capital I, this much amount of current is enclosed by considered Amperian loop, correct? See, which are the currents which are passing through this part of the turns, they are all enclosed by this outer Amperian loop, correct? Fine. Now, because the magnitude of magnetic field at each point on this considered Amperian loop is same, I can take it as constant, and so I can take it out of this symbol of integration. B is taken out. Now it is closed line integration of dl. Closed line integration of only dl now. And cos 0 is 1. Come on, mu 0 as it is, n into I as it is. B as it is now. B as it is. What do you mean by closed line integration of dl? That is summation of lengths of all the length elements chosen over considered Amperian loop. When you add the lengths of all the length elements which are chosen on the considered Amperian loop, naturally it will give you circumference of this circular Amperian loop. And for any circle, what is the circumference? 2 pi into radius. 2 pi into radius, correct? Fine. And now tell me this right hand side as it is, mu 0 n I as it is. Find out B, make it subject of the equation. This mu 0 as it is, this 2 pi r, I just transfer it on the denominator on the right hand side, n upon 2 pi r into I. This mu 0 as it is. What do you mean by n upon 2 pi r? It will give you number of turns per unit length of circumference of a toroid. Let it be shown by symbol small n. This capital I as it is. What is small n? I repeat, it is capital N upon 2 pi r. That is total number of turns which are wound on the circumference of a toroid divided by length of circumference, correct? It will give you number of turns per unit length of circumference of a toroid shown by symbol small n. My dears, though you are getting similar formula like this, there is different interpretation for this symbol small n appearing in both the formula. This is the formula to be used for extremely long current carrying solenoid, where small n means number of turns per unit length of a solenoid, and here for toroid, this small n means number of turns per unit length of circumference of a toroid. Right? Fine. Now, what is the physical importance of this device? What is its use? What is its application? I am showing you. We have prepared one device. It is called Tokamak, in which we store plasma, but that storage is possible only in that sort of magnetic field which has circular magnetic field lines in the limited region, and that sort of magnetic field we can get using toroid. So, toroid is very useful in the device called Tokamak for the confinement of plasma. Okay? And there in this device we undergo the process called nuclear fusion. That is, when two or more than two lighter nuclei combine, in that process some mass decreases, and that mass which is decreased is converted in the energy, and ultimately that energy is getting released. A process in which two or more than two lighter nuclei combine and they form heavy nucleus, at that time some mass which is getting decreased gets converted into energy. This process is called nuclear fusion, about which you will be taught in detail in 4th semester. Got it? Fine. Now we go for question number 13. What is Ampere's observation? My dears, Mr. Oersted in the year 1819 had made one very important observation, about which we had seen in the beginning of this chapter. What was that? Whenever we pass current through any conducting wire, we get magnetic field in the surrounding region. Correct? Fine. As soon as this news were declared all over the world, almost in the same time, after a week or so, there was a person working in the same field. It was none but Mr. Ampere, and that Ampere was interested in this fact. What did he do after that? He also had made one very important observation. What was that? He had taken two extremely long, thin, parallel, straight conducting wires, and then after, through such a pair of wires, when he had passed current in the same direction, he observed that there is attraction between two wires, and then after, when he had passed current in opposite directions, he noticed that two wires started repelling each other. So, when currents are passed in the same direction, there is attraction. When currents are passed in opposite direction, there is a repulsion. But then this Ampere's observation is not explained in the textbook. Why it happens like that? Now I would like to explain you in detail. Just look in the figure carefully now. Take this as wire number 1. Okay? Just take it extremely long and straight. Parallel to that is another wire, wire number 2. It is also extremely long and straight. Okay? Fine. Now we pass currents I1 and I2 respectively through them in same direction. Now just consider 3 points, say points P, Q and R. Where is point P? On the left side of both the wires, correct? Where is point R? On the right side of both the wires. But where is point Q? It is at the midpoint. It is at the midpoint in the region between these two wires. Okay, fine. Now these 2 points P and Q are equidistant from this wire. Let that perpendicular distance be small y. Now tell me, when you pass current I1 through the first wire, you will have magnetic field line circular, correct? And when you draw tangent at a given point on that circular magnetic field line, you will get direction of magnetic field. At this point, that magnetic field will be perpendicularly inside the plane of the figure. So I am putting cross. At this point, it will be perpendicularly outside the plane of the figure. I am putting dot. I hope you have understood the directions. No? Look here. Hold this wire in your right hand palm such that thumb should point in the direction of current. Then, in whichever manner the fingers of right hand palm take the turn around that wire, in the same fashion the magnetic field lines also take the turn around that wire, correct? So from here the tangent will be inside, that's why I am putting cross, and from here the tangent will be coming outside the plane of the figure, so I am putting dot, correct? The magnitude of magnetic field due to the current passing through first wire, I am just taking by symbol B1, here also B1, correct? Because these 2 points are equidistant from this wire. So these two magnitudes of magnetic fields are same. Now tell me, if you find out the direction of magnetic field at these points Q and R due to current I2 through second wire, then here it is perpendicularly outside, so I am putting dot. It is perpendicularly inside, so I am putting cross. I hope you understood. No, look here. Hold this second wire in your right hand palm such that thumb should point in the direction of current. And now when you just give the turn to the fingers this way, in the same manner the magnetic field line also take the turn, correct? So at this very point the tangent will be inside, so I am putting cross, and through this very point tangent will be coming outside, that's why I am putting dot, correct? And because these 2 points are equidistant from this second wire, the magnitude of magnetic field will be same, let it be B2, correct? Now tell me, what will be resultant magnitude of magnetic field at this point Q? Look, at this point direction of vector B1 is inside, direction of vector B2 is outside, and because both the directions are in opposite directions, naturally the resultant magnetic field will be subtraction of two values, correct? If I1 is greater than I2, if we assume I1 greater than I2, then B1 will be greater than B2, correct? If I1 is greater than I2, then B1 will be greater than B2. In that case, because B1 is greater than B2, we should write the resultant magnitude this way, B1 minus B2, B1 minus B2. Why minus? Because of opposite directions, okay? Here, because of subtraction of two magnitudes, the magnetic field is weaker, and compared to that, here magnetic field is stronger. Now, from a stronger magnetic field to weaker magnetic field, there will be some magnetic force exerted on both the wires. On this wire, from stronger to weaker magnetic field, magnetic force is exerted this way. On this wire, from stronger to weaker magnetic field, the magnetic force is exerted this way. Now look at these two directions. These two magnetic forces are exerted on the two wires such that they will force the two wires to approach each other, correct? So they will go closer towards each other. That's why you can say there is some attraction. That's why they are going closer, correct? But when there is attraction between those wires, provided you are passing currents in the same direction. So when we pass currents in the same direction through a pair of parallel, extremely long, thin, straight wires, then there is some attraction. There is some attraction, okay? Now, if you pass current in opposite direction, we find there is some repulsion between them. Why? I am showing you. Consider this as wire number 1, this as wire number 2. As usual, we take currents I1 and I2 through first and second wire, but you can see the direction now. I1 is flowing vertically upwards, I2 is flowing vertically downwards. Means these two currents are in opposite directions, okay? Like previous condition, you can think of 3 points, P, Q and R. Come on, P, Q and R. Tell me, if you find out direction of magnetic field at points P and Q due to current I1 in the first wire, here it is perpendicularly outside, here it is perpendicularly inside. How? Hold this current carrying wire in your right hand palm such that this thumb should point in the direction of current, and fingers are taking turn this way, correct? So from here it is going inside, so I am putting cross. From here is coming outside, so I am putting dot, correct? Similarly, if you find out direction of magnetic field at points Q and R because of current I2 through second wire, you will get it this way. At point Q it is perpendicularly inside, so I am putting cross. At point R it is perpendicularly outside, then I am putting dot. Hold this wire in your right hand palm such that thumb should point in the direction of current. Right now it is vertically downwards, okay? Then fingers are taking turn this way, correct? So from here it is going inside, and then from here it will come out. It will be coming out, so I am putting dot. Got it? Now tell me, at this very point you can see both the magnetic fields have got same direction, then addition, same direction, then addition. So here I am writing B1 plus B2, correct? Earlier it was B1 minus B2 because of opposite direction. Here it is B1 plus B2 because of same direction. So here you will get stronger magnetic field as compared to this and this, okay? And I told you magnetic force will be exerted on the current carrying wire in a direction from stronger to weaker magnetic field. Here magnetic field is stronger, here it is weaker. So magnetic force exerted on first wire will be like this, correct? Here there is a stronger magnetic field, here there is a weaker magnetic field. Magnetic force exerted on second wire will be like this, correct? So now look at these two directions simultaneously, then you will realize that those two magnetic forces are exerted on the two wires in such a manner that two wires will be compelled to move away from each other. Why are they moving away from each other? There must be some repulsion between them. That is why they are moving away from each other. Got it? But when it happened like that, when you had passed currents in opposite directions. Got it? So now let us summarize. When currents are passed through two extremely long parallel thin straight wires in the same direction, there is some attraction between them, and if currents are passed in opposite direction, then there is repulsion between them. Same direction of current will produce attraction, opposite directions of current will produce repulsion. Please remember, okay? Fine. Now we go for question number 14. It is about Amperes law. Earlier it was Amperes observation. Now we go for Amperes law. What is that? I am showing you. Consider some uniform magnetic field, say vector capital B. We call it external magnetic field, okay? And because it is uniform, you must show all these magnetic field lines parallel to each other. Not only that, perpendicular separation between each two consecutive lines also must be shown same. Now in this external uniform magnetic field, I just consider some straight conducting wire through which I am passing I amount of current, say in this direction. Now in the direction of current, if you consider current element, let it be I vector dl, correct? If you consider extremely small length, we call it length element, and if you take it as a vector in the direction of current, we call it length element vector. We show it by symbol vector dl, and then if you multiply by I, the term is called current element. Fine. Now because of this current, it has its own magnetic field in the surrounding region. Now there is interaction between that produced the magnetic field and already applied external magnetic field. There is some interaction, and because of that interaction, there is some magnetic force which is arisen and which is exerted on this current element. On this current element, whatever is the magnetic force exerted, I am showing it by symbol vector df. But in which direction is it exerted and of what magnitude, that was obtained by Mr. Ampere. In his memory, that result is known as Amperes law. How much is that magnetic force? It is this much, vector df equals to I vector dl cross vector b. This very result itself is known as Amperes law. How would you give the statement of this law? Very simple. Whenever a current element I vector dl is placed in some external magnetic field vector b, magnetic force exerted on it is vector df equals to I vector dl cross vector b, full stop. This very result is called Amperes law. I repeat, whenever a current element I vector dl is placed in some external magnetic field vector b, then magnetic force exerted on it is vector df equals to I vector dl cross vector b, full stop. This very statement is called Amperes law, correct? Now just take integration on both the sides, because I want resultant magnetic force exerted on the entire wire, okay? Take integration on both the sides. Integration vector df, that equals to integration of I vector dl cross vector b. vector addition of partial magnetic forces will give you definitely resultant magnetic force, let it be vector F, and because I is constant, I can take it out of this symbol of integration. I is taken out, left is integration vector dl cross vector B. But integration vector dl will give you total length vector, let it be vector L cross vector B. Integration vector dl is replaced by vector L, which is called length vector. It is to be taken in the direction of current. Okay. Now, if you want to have direction of vector F, you can definitely find out direction of vector L cross vector B, and that you can find out using law of right-handed screw, which you have studied in first semester. But compared to that law, the rule which I am showing now is very easy. It is called right hand palm rule. What is the right hand palm rule? Very easy. Look here. Expand the palm of right hand. In such a manner such that fingers should point in the direction of magnetic field and thumb should point in the direction of current. In this case, whatever is the direction shown by the perpendicular coming out of the palm of that right hand will give us direction of magnetic force exerted on a current carrying wire. I repeat, expand the palm of right hand such that fingers should point in the direction of magnetic field and thumb should point in the direction of current. Full stop. Now, a perpendicular coming out of the palm of right hand gives us direction of magnetic force exerted on that current element or exerted on that current carrying wire. Okay. I repeat for the last time. Expand the palm of right hand such that fingers should point in the direction of magnetic field, thumb should point in the direction of current. Now, think of a perpendicular coming out of the palm of right hand, which will give us direction of magnetic force exerted on the wire. Got it? Fine. Now, if you want magnitude of this, it will be F equals to ILB sin theta, correct? Where theta will be angle between vector L and vector B. Remember, direction of vector L means direction of current. So, whatever is the angle between direction of current and magnetic field, that is theta. Got it? Now, from this we can make out if any wire is to be exerted upon by magnetic force, three conditions must be fulfilled. First, it must carry some current. It must be present in some external magnetic field, and the length of that wire should not be parallel or anti-parallel with magnetic field, because if it is parallel or anti-parallel with magnetic field, then theta will be either 0 degree or 180 degree. In that case, sin theta will be 0. Okay. If there is no current through the wire, I will be 0, then F is 0. If it is not placed in external magnetic field, then B is 0, then F is 0. If it is placed parallel to the, length of the wire is parallel to the magnetic field or anti-parallel to the magnetic field, then theta is either 0 degree or 180 degree, then sin theta will be 0, F will be 0. Okay. So, remember, when a magnetic force will be exerted on a wire under three conditions, remember all the three conditions. First, if that wire carries some current. Second, if that wire is placed in some external magnetic field, and if its length is not parallel or not anti-parallel to the magnetic field, then and then only some magnetic force will be exerted on that wire, otherwise not. Got it?